the rubber band car. The purpose behind our project was to find the spring constant of rubber bands. And what better way to do that than to design and build a simple rubber band powered car? There were 3 major steps in our design process. First up, inspiration and research. There are tons of things in our modern world that utilize springs to store and release energy, like roller coasters, toasters, and the basis for our project, pullback cars. All of these things involve relatively complicated and therefore difficult to study mechanisms, so we decided to simplify things down to the basics and build our own rubber band powered car. Which brings us to step 2. Materials and design. To keep our costs low, we used a few household items to build our car. We used bottle caps for the wheels and added hot glue ridges to discourage slippage. Wooden dowels and straws made up the basis for our axles. Popsicle sticks forms the body, and we held everything together with a generous helping of hot glue. Due to the circumstances of our testing environment and the limitations of this project, some assumptions had to be made in order to complete our calculations. We assumed that air resistance was negligible and therefore omitted it from our calculations. We also assumed that the road and wheels had a constant coefficient of friction while the car moved, and most importantly, that the rubber bands acted like perfect springs. While analyzing our results, we also had to keep in mind some constraints, especially that we did not know the exact coefficient of friction between our wheels and the road, nor did we have precise measurements due to using just a measuring tape and a ruler to measure the distance traveled. Step 3. Prototype and adjustment. While building our car, we did run into issues with slippage from the wheels. To combat this, we added hot glue treads and some heavy household items to add weight to the car. Now here we go to our experiment process. Step 1. Calculations. I know it sounds boring, but this stuff is important. Now, we need to use what we have, distance traveled, time, and mass, to find what we want to know, the spring constant of rubber bands. Let's start with this simple kinematic equation. We can already cancel out our V initial times t because we know that our V initial will equal 0. From there, we can rewrite our equation to solve for acceleration and set it aside for now. Now onto our forces. Everyone knows Newton's second law, the sum of force equals mass times acceleration, and that will come in really handy here. So we will keep that in mind, but set it aside for now. One thing we also know to be true is that the sum of forces in our system is equal to the force provided by the spring minus the force of kinetic friction on the car. Since we have 2 equations that equal the sum of F, we can substitute one into the other to get this equation. Then we can rewrite it to solve for the force of the spring. We also know that the force of kinetic friction is equal to mu of k times mass times gravity, so we can substitute that in as well. We can set this equation aside for now and bring in another spring force equation. From this equation, we can solve for the spring constant by utilizing our previously derived equations. We also have to figure out our winding distance so we can compare it to our results. This is relatively simple because we can use our radii of both the wheels and the axles to solve for W. We also have to add 2 centimeters to our W value because in order for the rubber band to fit in our car, it had to initially be stretched 2 centimeters before winding up. Now, on to the fun part.
So going into the experiment, we put our car on the road and we put next to it 2 different measuring devices, just a measuring tape and a ruler, so we can see how much we winded the car and how much it traveled after we let it go. And we tested 2 different rubber bands. Rubber band number 1 was a bit stiffer than rubber band number 2, but they were both the same length. So gathering our data, we have our winding position, initial and final, and the position it was after it traveled, as well as seconds. And I used Excel to do the adding and subtracting for me here for total winding distance and total distance traveled for rubber band 1 and rubber band 2. Some additional things we needed was that both rubber bands had to be stretched 2 centimeters to be put in the position before it was winded. And then we have the radius of the wheels and radius of the dowel, which of course we need for our calculations, and the mass of the car. Some patterns that I noticed with the data is that rubber band 1, it moved a lot more then you wound it, whereas rubber band 2, you had to wind it more for it to travel a similar distance. For final calculations, we have for rubber band 1 a range of the K value from 20.7 to 30.7 newtons per meter, and for rubber band 2 we had a range of 17.1 to 18.4 newton per meter. And on here you can just see an example of one of the calculations that was done. Pretty much just what the other calculation slide said, but plugging in the numbers that we had found. So going into our analysis, I decided to put all of the K values for each trial on a graph, and what we would want to see is just a flat line. Each trial has the exact same K value, and of course that isn't the case. Both have a bit of a slope, and if you look at the K value for rubber band number 2, we have a lot more. They're a lot closer together than for rubber band number 1. Now, I suspect this is because since rubber band 1 was stiffer and gave more force, that there might have been a little bit of sliding taking place, especially for the trials where I wound it a lot more. And so because of that, I feel like there was some error for rubber band 1. Now, for other possible errors in our calculation that might have skewed the number, we have the accuracy and precision of measurements. I was just looking at the measuring tape and, eye is not perfect. Every road is different. The road in my neighborhood has very freshly paved asphalt, but something older might have a slightly different coefficient of friction. Another possible error, of course, is that our bottle cap tires are not actual tires and therefore don't have the same coefficient of friction with the road as actual tires would. And like I was saying before, sliding could still occur, and I think it probably did occur slightly with rubber band number 1. In conclusion, we had to use a lot of creative engineering to build our car, and a lot of problem solving took place. For example, for the weight distribution, we used these Allen wrenches on either side to give it some weight, and then for the top here, we needed extra weight. So what I did was, this is like a faucet adapter, and I filled it with a ton of tiny screws that I had laying around, and I taped it with electrical tape and made a little weight to put in the front here. Now, if I were to do this again with more budget and better tools, some factors that I would change so that we get a more accurate K value would be to lessen the friction right here between the straw and the dowel. I feel like we do have a loss of energy there. Making sure that the weight distribution is more even throughout the car as well, and having the bottle cap tires be even rougher so there wouldn't be a chance of sliding. And overall, this project was a lot of fun to do and a lot of fun to make. And yeah, thank you so much for watching.